All right, another lovely day up here in the Keweenaw. Finally had some summer weather this last weekend, which is a nice change of pace. Um, let's see, going forward, kind of giving you a plan and reminder of where things are going for the next couple of days. I have quizzes and homework to hand back. All of that stuff was graded on Friday, so in alphabetical order as always. We'll take a look at the quizzes when we get back, or once they've gone around. I think the question that was graded for correctness on the homework was number 525. I've been using a random number generator online to pick the one that I grade, so more so than in previous semesters, it is truly random which one actually, and they claim that the random numbers come from atmospheric noise, so whatever. So that one was the one that was graded for correctness. Everything else was graded for completeness. Grades should be up on Blackboard. If you're not seeing them, that means that I screwed up on the on the settings for the grade column, and I need to go and change that. But let's see. Homework, we've got one question we'll look at least a little bit. If there are other questions, we can take a look at those as well. But there was one specific question that an online student had. There's an exam that's tentatively scheduled for a week from today. Should be another evening exam in a week. So I think that should be fine. There shouldn't be a reason why you're looking. Yeah, well, Enterprise got scheduled after exams were picked out. So if you guys aren't there, I won't be either. So what can I say? So that should be fine. There's nothing else that there will be plenty of material to cover since we looked at the more advanced Thevenin circuits. We looked at capacitors and inductors. We looked at first order circuits. We'll definitely be done with second order circuits, and we'll be also ready to move into AC analysis, which I think we'll probably even get into today unless things take a little too long. So we'll have AC analysis, and that'll keep us busy for a while. So that'll put a decent chunk of stuff into the exam. Homework, just as what we're going to say is just so that you have plenty of time. We'll make it due at the beginning of class on Wednesday. Just one extra day to work on it so that you have plenty of time to digest the material from today's class on second order circuits and be able to go there. So homework due on Wednesday, beginning of class. So let's go in order. Let's do the quizzes. Then we'll look at homework questions. Then we'll finish up the material from the chapter. Then we'll see where we're at, what time it is, and all that kind of stuff. Other announcement kinds of things, I would expect to see a quiz definitely tomorrow, and perhaps another one on Thursday as well. So just as a bit of a heads up, I suppose. Okay, the quiz. I had hoped that this was going to be easier than it ended up being. People seemed to struggle a little bit with it. But, and I'd worked to make sure that everything would work out in a kind of a nice way so that the numbers would be nice and easy looking, and that the analysis would never be too difficult. And for one thing, that's why in the circuit as it exists on the paper, there's an additional resistor that I hadn't planned on putting in there, but it simplified the mesh analysis for solving for the for the short circuit current, and so I left it in there. So here's what the circuit looks like regardless of whether you were on campus or off. The only difference is some of the numbers will change slightly, but the makeup of the circuit was the same. So off-campus students or online students, you can just you can do all of the same analysis in all of the same way and just change the numbers and rerun them. But so that's a circuit that we wanted to find a Thevenin equivalent for because of the dependent source. We end up having to kind of go the long way and calculate both the open circuit voltage as well as the short circuit current in order to calculate what the Thevenin resistance was. That was one thing that I saw from a couple of people that was a little disappointing, was that when you do see these dependent sources, we can't just zero out the sources and then find out what the equivalent resistance is looking in from the terminals of the load. In this case, it's always going to be the ratio of a voltage to a current. And in circuits that contain only dependent sources, you're going to have to hook up the test source. But in circuits that contain a mixture, you'll have to solve for both the open circuit voltage and the short circuit current in order to find out what the ratio is and what the Thevenin resistance is. So we can remove the load and find out what's going on in the rest of the circuit. And so we get the 6-volt source still hanging out. We have the 12K resistor. We have the dependent source. And the 3K resistor hanging off here. This is going to be our open circuit voltage. It's notable that because of the configuration of the circuit, there is no current flowing through the 3K resistor. If there's no current flowing through it, then there's no voltage across it. And what that means is that the open circuit voltage is simply equal to negative 3Vx. So whatever you solve for is being the voltage produced by that dependent source that will give you the voltage, the open circuit voltage itself. There's there's a number of different ways that you could do this. You could do it as a nodal analysis. You could do it as whatever. The way that I chose to do it was essentially just writing a KVL around this loop to solve for what Vx actually equals. So you have negative 6 plus, and here's where I took a bit of a shortcut and I don't know why I did it this way when I was generating the solution, but it really makes life easy to say, well, this is 12K times some current that's flowing around I, but I don't really care what I is. I just want to know what Vx is. That's my end goal. So let's just put Vx in there. Minus 3Vx equals 0. And so more or less, now you combine terms, put the 6 on the other side, and you get negative 2Vx equals 6. Vx equals negative 3 volts. And so you should get the same answer if you did include all of this stuff with saying, well, Vx equals 12K times I, and then you stick in the 3K or 12K times I times 3 to get where the voltage source is and all that stuff. But this just gets you there in one less step. So we've got the voltage, what Vx actually equals. So we can plug that in over here. So that's negative 3 times negative 3. Or the open circuit voltage is just 9 volts. So that's the open circuit voltage. That's the first thing that we needed to solve for. Kind of set that aside and come back to it. On the I think the only difference on the online exam or the online quiz was that this was 12 volts and this was 5 Vx. And this had a different resistor value, but the analysis would be the same. You have negative 12 plus Vx minus 5 Vx, and it was 4 Vx equals 12, or negative 4 Vx equals 12. So not a huge difference there. But so now we solve for the short circuit current because we can't just solve direct. We can't zero out the sources. Here's another thing where I tried to make sure that the circuit would not be too difficult to analyze, and I included this 3K resistor so that there was something happening in the right-hand loop, because I'm honestly not sure how to write a KVL equation around this loop if there is no resistor over there, because you'd have something like positive 3Vx equals 0, and that would, I guess, theoretically mean that Vx equals 0, which I really don't know how that fits into the rest of the analysis. It might work out okay, but I would be a little, I didn't like the looks of what I was seeing when I was writing the problem, and so I tried to make it a little easier. So we can do, again, any way that we want. I think that a mesh analysis makes the most sense because we're solving for the short circuit current. So we can introduce our two analysis currents, I1 and I2. And I2 equals our short circuit current, so whatever we solve for there. So we've got -6 plus, and essentially you can do this the same way, that we've got Vx minus 3Vx equals 0. So we still have that, in this case, the -2Vx equals 6, or Vx equals -3. And we do need that at least for the second equation going around the right-hand loop, which is 3Vx plus 3K times I2 equals 0. So we can stick in the -3 up here, so we get -9 plus 3K times I2 equals 0. 3K I2 equals 9, and so I2 equals 3 milliamps. So again, I tried really hard to make sure that these numbers would come out in very nice ways. So we found an open circuit voltage of something. It was 9. One of the things that I noticed when I went through my solution very quickly was that I had originally solved for an open circuit voltage that was -9 volts. And when I double checked that work, I said, well, if nothing else, it doesn't make sense to have a negative open circuit voltage if I have a positive short circuit current, because that ratio would give me a negative resistance, and I don't think that that has any meaning. So it was good for me to go back and double check the work that I had done for my open circuit voltage and verify the sign on that. So the open circuit voltage was 9. The short circuit current was 3 milliamps. And so the Thevenin resistance is just 3 kiloohms, which is the 9 volts divided by the 3 milliamps, for what it's worth. So that was the quiz. I was hoping that it would be more simple than it apparently turned out to be for at least some people, but any questions on that? I would assume that any questions on the exam would be maybe that I think that I would probably put one more loop into the circuit, whether it was up on the top or a third loop off on the left or right hand side, something like that. It would be somewhere, but and that might make the analysis somewhat simpler for you. I don't know, but so you should be able to do that. It's something that will show up on the exam on Monday. So okay, if you do have any questions on that, please come and see me. Life will be slowly getting finally back to normal, I think, for the rest of the summer here, as I just start hopefully preparing for the fall. I don't know. So homework. I did have one specific question on the homework. And so I wanted to take a look at that at least very quickly. So this is homework problem number 747. The circuit as given in the problem is up on the top. And the primary question that was asked was, how do we get this down to the single capacitor that we kind of know how to deal with? And I think my guess is that people were overthinking it maybe a little bit too much. That it's just really that the 600 and the 300 microfarad capacitors are in series with each other, and that series combination is in parallel with the 200 microfarad capacitor. And that when you combine all of those, it reduces it down to this pretty simple circuit. And the only question is, what is the equivalent capacitance that that we'll actually use in our first order analysis? So that switch closes at time equals 0. It will be a fairly odd circuit, I suppose, if you're really looking at the configuration, but shouldn't be too weird. But that equivalent capacitance, remember, capacitors combine in series, like resistors combine in parallel. So we have 1 over 600 microfarads plus 1 over 300 microfarads, which should give us 200 microfarads. As long as this, is that right? So it should be fine. And then once you've gotten these down to the single capacitor, the 200 here and the 200 here will be in parallel with each other, and so they combine in parallel like resistors combine in series, or just that final equivalent capacitance will just be 200 microfarads plus another 200 microfarads. And so now you have a value you can stick in there and you can start doing your analysis on it. Any other questions on that one, or any other questions on the homework in general? I can imagine how this one could be a little weird in terms of figuring out exactly where all the current flows and whatnot. It may be helpful to try to redraw that circuit, because if you try to visualize it without the switch in there, and without kind of trying to reorient some of the elements, you have that voltage source and this current source over here and resistor, and then these two resistors over here. Whoops, one there, and we're solving for the voltage across the 2K resistors. So I can imagine that would be a little awkward without trying to redraw the circuit at least a little bit, but so consider doing that. It may even actually be easier to combine these two 2K resistors down to a single 4K resistor, which may make the circuit easier to redraw. Again, like I mentioned before, I have a really hard time kind of reorienting things and seeing exactly what's in parallel with what, but essentially all I guess you could kind of get it down to something like the voltage source with the 2K and something like this, I think, should be a fairly decent representation of the same circuit. If this is a 4K resistor, which is a combination of the two 2K resistors, I think that should be reasonable. But because the the combination of these three elements in series should be in parallel with the current source, and that should be in parallel with the resistor as well. And I think that's what I've represented. The one thing to be really careful about is the polarity of the voltage source. I'm not feeling 100% on that one, but so just double check that one. Any other homework questions that people have? Okay, so let's then finish up the material that we were talking about on last Thursday, which is dealing with second order circuits. So to review the stuff that we did talk about on the PowerPoint slides over here, we've got the second order RLC circuits. For the most part, again, we're going to keep the analysis at a relatively high level here. And it's going to mostly be a very cookie cutter formulaic way of analyzing these circuits. And they're called second order circuits because they behave like, or the solution to any one of the voltages or currents in the circuit is characterized by a second order differential equation. But generally, we will use a somewhat more, again, formulaic approach to solving them. Parallel RLC circuits, we use this as the easy way of showing that it is a second order differential equation, but primarily we're going to be thinking about it in terms of the characteristic equation. And the characteristic equation, or the roots of that characteristic equation, are what we'll use to do most of our solutions, with the coefficient on the first order S term as 1 over RC, and the constant term being 1 over LC. And so solving for the roots and these parameters alpha and omega naught give us a lot of the power that we need to do our final analysis. If you look in the textbook, you're not going to see the same material as what I've been working through, and it's largely because I don't like that material, and that's not how I learned it. And I don't, from what I can tell from looking at Dr. Imbardar's stuff, he also doesn't teach it using the zeta or the squiggle from our textbook. He uses the same kind of alpha and omega naught stuff that Nilsson and Riedel use in their textbook. But so alpha gives us the Neper frequency, and it's solved for as 1 over 2 RC. Omega naught is the resonant radian frequency, which is a square root of 1, or is equal to 1 over the square root of LC. In a couple of chapters, we'll see omega naught come back again as we start looking at more resonant radian frequency stuff, and as we start looking at AC circuits. But so solving for those two things gives us a lot of the information about exactly how the circuit behaves. And you can plug those into these equations. S equals negative alpha plus or minus the square root of alpha squared minus omega naught squared. And that gives you what the roots are. You don't always have to solve for the roots, though, because especially in the underdamped case, the roots don't actually factor into the final equation. But anyways, you can use them to find out whether the circuit is going to be overdamped, underdamped, or critically damped. And there's a relationship between alpha and omega naught that tells us which of these has actually occurred. Zeta itself can tell us this as well. I think if zeta is exactly 1, that means it's critically damped. If it's less than 1, it's overdamped. If it's greater than 1, it's underdamped. But I think it's a lot easier to just use the relationship between alpha and omega naught. This is what a graph of those look like, with the underdamped case exhibiting something that we call ringing as it attempts to settle down. And if you look at the form of the solution, you have this cosine term and a sine term in the underdamped case, which helps kind of explain where that ringing comes from and that sinusoidal behavior shows up from. But So if omega naught is greater than alpha, or is less than alpha squared, then the circuit is overdamped. If omega naught squared is greater than alpha squared, then the circuit is underdamped. If they equal each other, then the circuit is critically damped. And the form of the damping tells us the form of our differential equation. So we did a quick example of finding what the roots in the damping look like. And we did 2 of the 3 cases in terms of the parallel overdamped and underdamped responses. The form of the overdamped response is V equals K1 e to the S1t and K2 e to the S2t. Normally the roots will show up as being negative, and so that shows you how they you get the decaying behavior anyways. K1 and K2 are constants that are solved for using initial conditions, using the equations at the bottom of the slide. V0 equals K1 plus K2. And then we use the second condition, which is the derivative of the first condition, to solve for the second one. Generally, in the case of most of the circuits that we see, we will just use circuit analysis if necessary, but normally that initial condition is just given to you in some way or another. So that was the overdamped response. In the underdamped response, the form of the roots is the complex conjugate, but you can kind of ignore that and not worry about it so much. Instead, just worry about solving for something called the omega d, or the damped frequency. Because omega d actually does show up in the response as opposed to the roots themselves. The form of the response has a cosine term as well as a sine term in it, and more direct, and then as well as the exponential stuff, b1 e to the negative alpha t and b2 e to the negative alpha t. B1 is really simple, it's just the initial voltage. B2 is solved for the same way as before, using the first derivative of the voltage, which is the current through the capacitor. And we use B1 and B2 instead of K1 and K2 to indicate that these are very different constants. They're not the same between these couple of different forms of the response. So we just barely squeezed in this example, and now we can look at the critically damped response. Critically damped is an interesting thing to kind of think about, and all of the same kinds of information show up. S1 and S2, because it's critically damped, the roots are the same, are equal, are real and equal, and you can solve for it either way. I mean, it'll be, the square root term goes away because you have the square root of 0. But you get negative alpha as both of the roots, which is negative 1 over 2 RC. Again, we have different constants, D1 and D2. In this case, D2 is equal to the initial condition, and D1 is solved for as D1 minus alpha D2 equals the current through the capacitor divided by the capacitance itself. We can do an example of showing critically damped stuff, and there may be some times where you will run into that in problems or whatever, but one of the things that we didn't really talk about in the resistor chapter or the capacitor chapter or inductor chapter, any of those, is that we work with all of these resistor values in our in these equations and stuff, and we're treating them as if they're very fixed numbers, and there's no doubt that this 1 kilo ohm resistor that I have in my circuit is exactly 1.0 kilo ohms for wherever. But that's not really the case. We have tolerances that factor into exactly what the value of the resistor is. And if you look, you'll get lots of experience doing this in the lab that goes along with this course, I guess probably next fall, where there are bands, colored bands painted on resistors that help you determine what the value of the resistor actually is. And I did not like trying to decode those bands all the time, especially when I got into the electronics lab. But the very first band, I think, are they gold, silver, and bronze or something like that? You guys familiar? And that gives you the tolerance on the resistor. And the tolerance is usually something on the order of like 1 to 5% or even 1 to 10%. And when you start thinking, well, what is 10% of a mega ohm or a kilo ohm, and that's a big variance. And for when you start looking at these parallel critically damped responses, for these things to work, all of the tolerances in the real circuit have to be the same, and these numbers have to work out exactly to get this parallel critical damped response to occur. And that just doesn't happen a whole lot in real life. It's a fun mathematical problem to do in class, but in terms of reality, it just doesn't happen that much. So we could do an example, but it's not hugely worth our time. So it works all of the same ways that we did the stuff before. Use the initial conditions to solve for the current and figure out what's going on there. So. The things for series circuits are slightly different, but only just a little bit. If you look at a simple a series RLC circuit, with some inductor, capacitor, and resistor, and some source voltage, whatever that happens to be. If we were to write a KVL equation going around this, what we would find is that the voltage across the resistor, which is R times I, plus the voltage across the capacitor, which is 1 over C times an integral from time t0 to t of I of x dx, plus some initial condition voltage at time 0, plus the inductor times the derivative of the current equals that source voltage. So there's our KVL equation around the loop, pretty ugly. We take the second derivative, or take the derivative with respect to time to get rid of this integral term, and we end up with L squared I over dt squared plus R di over dt plus, let's call it 1 over C times, that shouldn't be an I don't think, that should be a 1. Equals the derivative of the voltage with respect to time. And so if you look at that from the point of view of the characteristic equation, get things kind of moved around in an appropriate way, you get that the roots are given as s squared plus r over L times s plus 1 over LC. And that is our characteristic equation. This is the one we're going to work with. Now the key thing to note about this characteristic equation, this is the same as it was in the parallel case, 1 over LC, and so solving for the the natural resonant radiant frequency is going to be exactly the same. It's going to be 1 over the square root of LC. But what is going to be different is solving for alpha will be different because the coefficient on the first order S term is different. So what does that look like? At least a little bit. The Neper frequency alpha in this case then is going to be R over 2L. That's an alpha. Wow. Alpha equals R over 2L. And then our resonant radiant frequency is the same as 1 over the square root of LC. So this is different from the parallel case. This is not. All of the solution techniques for dealing with series RLC circuits are the same as dealing with parallel RLC circuits. I don't spend a lot of time on it because I mean, the parallel stuff gives me at least as much understanding as the series stuff. But for what it's worth, here's the forms of all of those equations. We have the overdamped case where omega naught squared is less than alpha squared, and that is a1 e to the s1t plus a2 e to the s2t, more or less the same as the first case, but again we use the slightly different equations. You can use the same equations or the same basic premise to solve for the initial conditions, except now what we're looking for is the current through the inductor is going to be our first order term, and our second order initial condition is going to be the voltage across the inductor. So, so that will help us solve for each one of our coefficients here, A1, A2, B1, B2, D1, D2. And there's something, one of the things that you don't have to try to like memorize, you don't have to memorize the forms of these equations. On any exam, I will give you all of these forms of the equations. I'll give you how to solve for alpha and omega naught, but what I won't do is tell you what the relationships are between alpha and omega naught, so you have to remember at least the overdamped, underdamped, critically damped stuff, so that so all the rest of these forms of the equations will show up on the cover page or a formula sheet for the exam. So one quick example of dealing with a series RLC circuit, just to give you some sort of idea of what's going on. We've got resistor, an inductor, and a capacitor, which by default makes it that RLC circuit. They're all in series with each other. There's some voltage across the capacitor. We have some current running through the circuit. And there's some current IL at time 0. The value of the resistor itself is 6 ohms. The inductor is a 1 Henry inductor, and the capacitor is 0.04 farads. Initial conditions that we're going to need, the initial charge on the capacitor, so Vc at 0 equals -4 volts, and IL of 0 equals 4 amps. So again, this is going to be our how we'll solve for the easiest one, which is this is our first order initial condition, and this we'll use to solve for the second order initial condition. Or so we can solve for alpha and omega naught, because that's, the first step in all of these analyses is always going to be doing that, at least once you have a circuit that looks like this and you've got your initial conditions. I think I should have picked at least one question in the chapter that did ask you to use, you had a voltage source or something hooked up that asked you to solve for the initial conditions using some basic circuit analysis stuff. But so alpha equals R over 2L in this case. So that is 6 over 2 times 1, or 3. And omega naught is 1 over the square root of LC, is 1 over the square root of 1 times 0.04. And so that means that that's 1 over the square root of 0.4. You can kind of do that in your head. That's 0.2 squared would give you 0.04. And so 1 over 0.2, which is 1 over 1/5, should give us 5 when we're done. So alpha squared equals 9, omega naught squared equals 25. And since omega naught squared is greater than alpha squared, this is an underdamped circuit. So the form of the solution will be the current with respect to time equals some constant b1 e to the negative alpha t cosine of omega d times t plus b2 e to the negative alpha t sine of omega d t. And omega d is solved for in exactly the same way. That still is solved for as the square root of omega naught squared minus alpha squared. So we can see that the numbers here were very carefully chosen because the square root of omega naught squared was 25 minus 9. That's 16. The square root of 16 is 4. So these are obviously incredibly contrived numbers, but hey, what not? Why not? So that's something to stick aside. Now we need to solve for our couple of for our constants b1 and b2. b1 equals is simply given as the initial condition of the current through the inductor. It used to be the voltage across the capacitor in the parallel case, but now we're looking at the current through the inductor, and that would be the same for all of the cases. But that was given as 4 amps. And then our other equation is negative alpha b1 plus I think it's omega d b2 equals some other initial condition. And so we need to know what that initial condition actually is. You have to do just a little bit of circuit analysis to find out what that's. And essentially what we're looking for is the initial voltage across the inductor. So we run around the circuits and to get some idea of what that is, do a nice KVL equation around the loop. So we have some initial voltage VL, which is what we're solving for. We have a voltage across the resistor and a voltage across the capacitor. And KVL says that equals 0, right? Well, we were given the initial voltage across the capacitor. That's negative 4. We need to solve for what the voltage is across the resistor. And let's rearrange the terms a little bit. So that's negative VR minus VC. And that tells us what the voltage across the inductor actually is. So the voltage across the resistor is negative whatever the current was, which was 4 amps, times the resistor, which was 6 ohms, and then minus the original voltage across the capacitor, which was negative 4, so that'll be plus 4. So that's negative 24 plus 4 is negative 20. So that's the initial voltage across the capacitor, or the inductor. So we can stick that up there. Continue the work over here. So negative alpha is negative 3 times b1 plus, let's see, omega d we solve for is 4 b2 equals negative 20. We can plug in that we already solved for b1, that was positive 4, so it's going to be negative 12 plus 4 times b2 equals negative 20. So that'll be adding 12 to both sides. We get 4 b2 equals negative 8. So b2 equals negative 2. So we have all the information that we need. We have omega d, we have alpha, which we solved for on the previous slide, which is 3. We have b1, we have omega d, which I already noted, and we have b1, or b2. So the final form of our circuit, the response will be b1 for e to the negative 3t cosine of 4t minus 2 e to the negative 3t times the sine of 4t.
Where did B1 come
Up here?
from? Yeah.
No, it's not always going to be the case that B1 equals omega d. In this case, this is coming from the initial current through the inductor, I sub L. It just happens in this case, unfortunately, in order to make the numbers kind of nice, they used 4 too much, essentially. If you remember back from the original statement of the problem, we had initial voltage across the capacitor of negative 4 volts. We had initial current through the inductor of 4 amps. And when we solved for omega d, it happened that it was also 4. And they were just going off of that whole 3, 4, 5 triangle inequality thing. So that is, how we ended up with the numbers that we did. And so, no, it's not always going to be the case that B1 will be the same as omega d. It just worked out in this case that happened. So that's doing the series case. Now, the key difference is instead of looking at initial conditions across the capacitor, we're more interested in initial conditions in the inductor for the series case. But otherwise, the solution techniques are pretty much the same. For the most part, I don't worry about series stuff nearly as much. And that is not just my opinion so much as I look through a whole bunch of circuits books, and everybody spends an awful lot of time saying, this is how the parallel circuits react, and then in like 2 pages, oh yeah, and this is what series stuff does too. They just don't seem to care as much. I don't know what the deal is. I think it's this idea that if you understand how to solve for the parallel case, then you pretty much get what you need to do for the series case. Maybe that's it, I don't know. But so that is it for this chapter. So you should be able to work on the homework, all of the problems tonight. If you have any questions, please ask them going into tomorrow. And yeah, so let's sum up the chapter. We did that one. So let's sum up the whole chapter as we go forward, because this is the end of our DC analysis. Woohoo! We get to do something a little different, and perhaps maybe a little bit more interesting. I don't know. So the basic summary of how we solve these circuits. For first order circuits, it is solved by the solution takes the form of a first order differential equation, but we normally do this step-by-step method in order to find the solution. The response will always be of the form k1 plus k2 e to the negative t over tau. And the circuit decays to less than 1% of its initial value after 5 tau seconds, which we use that fact to figure out what's going on in terms of settling down. The time constant tau is solved for as the Thevenin resistance times the capacitance in an RC circuit. In an RL circuit, and I don't know why I constantly put LC around, but in an RL circuit, tau is given as L over the Thevenin resistance. So we have a step-by-step process to solve it. That solution process is that we look and we find what is the initial condition across the storage elements just before the switch has been thrown. So what is the voltage across the capacitor? What is the current through the inductor? Once we know that, we will draw the circuit just after the switch has been thrown, and we will stick in either a voltage source for the capacitor or a current source for the inductor, which will allow us to solve for the condition across whatever we're interested in, whether that's a voltage or a current or whatever, as a, right after the switch changes position. And we can do that because we cannot have the voltage across the capacitor changing instantaneously, and we cannot have the current through an inductor changing instantaneously. So once we've done that, we've solved for the initial version of that. We'll redraw the circuit at time equals infinity, or time greater than 5 tau at least, with the storage elements again exhibiting its steady state behavior, either shorting out or opening up, and solving for the condition again. We'll solve for the Thevenin resistance, and that may be just zeroing out the sources, or it may be we need to solve for the open circuit voltage and short circuit current, but something to be aware of. And once we have all of that, we can plug those into our equations and find out what the circuit actually looks like, or what the response actually looks like. Second order circuits contain a capacitor and an inductor. The characteristic equation is that s squared plus 2 alpha s plus omega naught squared. We'll solve for alpha and omega naught as a normal part of our solution. And the relationship between alpha and omega naught is going to tell us whether the circuit is overdamped, underdamped, or critically damped. And that will give us the form of the solution, which again will be handed to you on a silver platter on a formula sheet attached to the exam, so you don't have to try to memorize those things. 2 initial conditions are needed for parallel circuits. That's normally going to be the voltage across the capacitor and the current through the capacitor. And for the series circuits, then you're going to need the current through the inductor and the voltage across the inductor. So you'll use those. You'll solve for the constants, and then go from there. So normally the circuits that I will give you for second order circuits will be they will look just like the kinds of circuits that we've seen in class. Simple parallel circuits where there's some easy known voltage across the capacitor, and you'll solve for the current running through it by doing a little bit of circuit analysis. If there's 4 volts across the capacitor, then there's 4 volts across the resistor, and that meant such and such a circuit was running, or such and such a current was running through the resistor. So, yeah. So that is chapter 7. And again, that is the end of our DC analysis. From here, we move on to AC analysis, which is where you need to be comfortable with the way your calculator deals with phasors, because we will spend most of our time quantifying the behavior of circuits using phasors instead of the time notation, for 2 reasons. Number one, it's a lot less work and it's much more compact, but it also is I think actually it really boils down to it just being a whole lot less work to write it down and keep track of what's going on, because we can also, to some extent, ignore the frequency stuff that's going on and just apply almost all of the same analysis techniques that we've learned. The only analysis thing that we've learned that doesn't have an application in AC analysis is first order and second order transient circuits, because what will end up happening is everything that we do will just basically look like, we'll be able to kind of treat it like a resistor. And so Thevenin analysis, node analysis, mesh analysis, we can just do all of those things, and instead of using just constant values, we'll use phasor values, and life will be mildly more complicated. The numbers will get messy extremely quickly, but some of the more complicated stuff is actually not that complicated. So I'm going to stand up to talk about some of these early slides. What are we talking about? In Chapter 8, we'll do just a very brief review of sinusoids and phasors so that you're up to speed on how this is going to work. And again, now's a good time to start if you haven't already looked at your calculator manual to find out how you're going to do phasors, now would be a good time to do that. We'll look at the phasor relationships for circuit elements themselves. So how do you represent what's called the impedance of a given circuit element, whether it's a resistor, an inductor, or capacitor, and what does that look like? How do we write that down? We'll look at that concept of impedance, which is kind of the great equalizer, and now we'll start, instead of thinking so much about just resistances and these inductances and capacitances, we're going to throw all that away and say we're going to work with this idea of an impedance, which is, we can just use a complex number to represent that, and no more derivatives. Derivatives go away. We'll look at phasor diagrams. You guys, do you look at phasor diagrams in DSP? A little bit? Yes? No? Do you remember DSP? For a lot of you, it was like just a couple weeks ago, wasn't it? Anyhow, we'll look at them. I'm not really great with phasor diagrams, and I don't like them myself. I don't find them to be particularly useful or enlightening in any way. But after I taught the course, I think the first time someone came back and said, well, we didn't talk about phasor diagrams and run the prereq exam for the circuit slab. And I'm like, all right, I will talk about these phasor diagrams, because I don't find them to be at all useful. And just like I also have never found the power triangle diagrams to be useful, but people were getting into power classes and looking at these triangles and going, I don't know what that is. So we'll look at those. I'm just not a visual person. I'm just not. But we'll look at some basic AC analysis using KCL and KVL, and then our other more advanced techniques, everything except for first order transient analysis, because the whole point behind transient analysis is that the circuit is now containing these inductors and capacitors, which gets rid of the nice linear current and voltage relationships. But we're going to bring those back, and impedance is going to be what lets us do that. So we're going to be able to analyze more advanced circuits that way. So the general form of any sine wave, and you could draw an arbitrary sine wave at this point if you wanted to, but it's got that sinusoidal behavior. You're familiar with what that looks like. And it has some sort of magnitude, and we'll call that x sub n, and it has some frequency, omega. And primarily when we talk about frequencies, we're almost always going to be dealing with them in terms of radians. There are odd conventions that are used when we talk about some of these things. For example, the radian frequency is what we're normally going to talk about in terms of that coefficient on the time variable, and we're almost always going to express that in radians per second. Occasionally, it's expressed as a frequency in hertz, but usually not. Usually it's in radians per second. But for whatever reason, the phase angle theta, which is that the last final form of the equation, that's not expressed in radians. That's expressed in degrees. Why? I don't know. They just did, and so you kind of got to get used to that. Just as a reminder, if you do see something, or you're given a circuit description and say, well, it's operating at 60 hertz, or it's operating at 100 hertz or something, and you want to put it into this kind of general form, you multiply that frequency times 2 pi, and that will get you the radian frequency. One that you should kind of get familiar with is 60 hertz. 60 hertz is the frequency that most of the magic outlets in the wall operate at. And that happens when you run the numbers, that turns into 377-ish. It's like 377.01 or something if you multiply 2 pi times 60. And so you'll see 377 show up as the radian frequency on an awful lot of our problems. And it's just kind of getting you used to working with the 60 hertz that is the frequency of our power system. If there are two sinusoids, this one does help a little bit more to have the picture. So draw this at least a little bit and try to make use of the colors as much as possible. So if we have two sinusoids and one of them goes like this, and it has that magnitude x sub m, and we could quantify this as some function x sub m times the sine of omega t plus theta. We could have some other, and just so that it's clear, we could have some other function that had the same magnitude even, but had a different phase angle. And we could quantify that one as being x sub m times the sine of omega t. Well, actually, those are the other way around, but it doesn't really matter a ton. It probably does, but obviously, if you have some sort of phase angle, it's not going to start at the origin when this one doesn't. But the point is that this one perhaps has some. Let's just change this one to be phi instead of theta. So that's phi, and we'll call this one, we'll say that it has a theta phase angle. So if you have two sinusoids with the respective phase angles, in this case theta and phi, in this case the first one, which is, so this one, the black one, the black solid one, leads the second, the dashed red one, by some phase angle, and it leads, so black leads red by theta minus phi radians or degrees or whatever, however they're expressed. We can also look at it, same information, that we can say that red lags black by the same number, theta minus phi radians.
So one.
Well, so I guess is that better?
If that's how you say it when you're using degrees, it's still unreadable.
Yeah, I'm copying to some extent off of my notes, which happens to say radians, but it's really whatever the way is that you're measuring the angle there. Normally it's going to be degrees, but it could be expressed in radians or whatever else. And the other terminology that if theta equals phi, or in other words, if there is no leading or lagging, those are called in phase. So that terminology will come back to us a little bit more later, especially when we start talking about power factors. But the next slide I put in there because the book thought, wow, these are some really useful identities. And perhaps the only one that's even remotely meaningful are the first two, which is that cosine and sine are 90 degrees different from each other. And all of the rest of them, if you use them, I would be really surprised. The only thing, the second pair isn't half bad, which is indicating that when I start grading these problems, I have to start being very careful because the answer that you get could be essentially the same answer that I get, but your calculator gives me a number that's 180 degrees out of phase with the answer that I got. And you know what? That's a-okay because you know, that's how cosine and sine work. I just have to be aware of that when I start writing these questions. But other than that, the only thing that's really meaningful is that we've got the difference between a cosine and a sine being 90 degrees, right? So if you have the sine, if you have the cosine, if you add 90 degrees or pi over 2 radians, that will get you to sine. If you have the cosine, or if you have the sine, you can subtract the pi over 2 or then subtract the 90 degrees and get your sine back. So, other than that, I spent a lot of time typing those into Microsoft Equation Editor and never ever use them. So, but they're there. Hey. So it may be you guys probably express most of your phasors in DSP as the e to the negative j theta form, I think. We're going to do it slightly different, but it's the notation that we use is going to be more or less the same as, we're just going to kind of throw away that e to the j theta, or e to the j part, and use a slightly different notation. So what you'll see is that if you have some sort of voltage, and I'm not going to bother to write it down when it's all up on the screen, what we'll say is if we have say a voltage source that gives out some magnitude of volts in terms of V sub m, and putting it out at some frequency omega and some phase angle theta, that the phasor representation of that will be V sub m at the angle of theta degrees. And I think that should be the same as saying V sub m e to the j theta. It's basically the same thing. And there's obviously, and you guys probably had to do it by hand or something, but there is that conversion back and forth between the phasor form, the e to the j theta, and the rectangular form, which is the 1 plus j whatever, or no. So you can have things in the phasor form, which would be something at V sub m at some angle theta. And you can also have it in the rectangular form, which is, say, A plus JB. And so those are the two forms that you'll kind of go back and forth between. There are, I have no idea why, again, some more odd traditions or that we hold to, or conventions that like voltage sources, most voltages, most currents, and power kinds of things are all expressed as phasors, but for whatever reason impedances are expressed in rectangular form. I don't know. And there's a relationship between those, and to be perfectly honest, I don't know what that is offhand, because I just use the arrow rect or arrow phasor button on my calculator to figure out what it is. For example, let's say we had let's see what mode I'm in these days. So I'm in rectangular. So let's say I have some voltage that's 12 volts at an angle of, say, 45 degrees. So a 12 at an angle of 45 degree voltage equals roughly 8.5 plus J 8.5. And that's a really horrible, it's actually like 8.49, 485, whatever. But that's the kind of conversion you'll do a lot, going back and forth between phasor and rectangular form. So that's how we're going to express our phasors, is this V with some magnitude at some phase angle with the little angly bracket thing in the middle. And I know that at some points I sat down with someone with a TI 89 and figured out what that syntax actually looks like on mine, on the 86, excuse me. I have a little button that allows me to type in the angle sign, and dealing with those is really easy. So for example, on my calculator, and I think this is the same on my wife's TI-85, I played around with hers a little bit. When I want to type that number in to my calculator, I just put a parenthesis, 12, angle 45, and that's how I type that number in. When I want to type this number in, I type 8.5, comma 8.5 and put them in parentheses. And that's how I do it in my 86, and I think that's how it works on the 85 as well. I think when it comes to the 89, so this is the 85 and the 86. On the 89, I think that you guys have a little bit more, perhaps, intuitive notation where you just say 8.5 plus I 8.5. I think you have an I button somewhere on your calculator that allows you to just type that in. The question that you have to kind of ask yourself is, what mode is my calculator in at the moment? I do not remember how you put that one in. What's that? Oh, okay, so there is an angle button right on the keypad.
Angle is second and double key.
Okay, so I guess you'll have to play with it and make sure that you're feeling comfortable with it, because to be perfectly honest, I have never done these things by hand, and I don't ever really want to. I usually rely on my calculator to give me pretty good answers when I'm dealing with it. So make sure you're feeling comfortable with that. If you're not, stop by and I can try to help you out on that one. So a couple quick examples of taking, one of the things that I forgot to mention when it comes to phasors. Technically, if we were to come back up here and say, well, here's this phasor voltage that's some magnitude at some angle. In the book, what they will do is they'll make sure that it's a nice bold letter, that there's some voltage that's this magnitude at this phase angle, right? And they'll use a bold character to indicate that. I will try, and I normally will put like an extra slash somewhere, or like make it look something like that. That would be a voltage, that would be a current. It's hard to always make it clear that what we're talking about is a phasor and not just a magnitude. So again, in the book, and when I write like quizzes and stuff, you will see you'll see phasors or other complex numbers given with a bold character as the variable name. But I'll kind of use this when I remember. I will try to use this kind of double slash thing when I'm writing them down. To be honest, I normally forget, and it's hard for me to remember to do it all the time. But that's another notation thing to be aware of. So, a couple of examples of taking time domain equations and turning them into phasor domains. We should be able to get through these pretty quickly. So we've got some function v1 of t, which is given as 12 times the cosine of 377t minus 425 degrees volts. And what is the phasor v1? What does that equal? The upshot here is that, again, we can almost do this so easy that it's dumb when we say, all right, well, that's 12 at an angle of negative 425 degrees. And now we have a phasor. I think normally we like to try to keep the phasor within the 0 to 360 degree range, but it's not a huge deal. One of the things that you do notice, though, is that this does throw away all of the frequency information. And so when you're going back from a phasor to a time domain function, you have to be aware that you need frequency information if you're going to figure out what that answer is. So let's do one of those real quick. If we have a phasor that's 10 at 20 degrees, what is, and the frequency equals 400 hertz, what is the time domain function? Well, the part that we know is that it's going to be 10 times the cosine of something times t plus 20 degrees. That much we know, but this part we still have to figure out, which is going to be 2 pi times 400, which is taking the frequency in hertz, turning it into a radian frequency, and in my notes I have it cheating as just calling it 800 pi times t. But you could always multiply 800 pi times, out and find out what that value is supposed to be. So we'll come back and we'll look at some more of that stuff later. We'll do a quick quiz tomorrow at the end of class, and it would be probably, I will try to make a very, very simple first order transient circuit. Yeah, I think that'll be what it is. And I will, again, work very hard to make sure that it looks nice and that the numbers are not too ugly. And then we'll come back to the AC analysis tomorrow in class. Homework is due at the beginning of class on Wednesday. Quiz tomorrow, like I said. Have a good one. We'll see you tomorrow.